Thank you. Thanks for the organizers for inviting me as well. Okay, so I want to talk about super-approximation and what it is and some of its applications. Today's lecture is going to be a bit more kind of survey of the recent results on this subject and some of the applications. This lecture will be like that. And okay, so and I confess that the order is going to be a bit unusual, but I hope that the order that I present the topics, the things, can help to unify some of these results, see the connections. So, okay, let's start with this. We start with a very general kind of setting, so general that it is hopeless, but nevertheless, then we look at the special cases. So what is this general setting? The general setting is that we have a compact group and we have a finitely generated subgroup of this compact group. So we are given actually a finite subset of G. And in this talk, I always assume that my generating set is symmetric, meaning it contains all the inverses of the elements. And I also assume that identity is here. Okay, sometimes I don't. Sometimes I assume that it is a union of two things and gamma is generated freely, but most of the times I assume this. And okay, so it's finite. And the general question that we want to understand is how the elements of gamma is distributed inside G. So this is a general question that you would like to understand. How is gamma distributed? In G. Okay, before I move on, before I actually say what it means, we should interpret it in mathematical sense. What I mean by this, I should say that classically you can think about circle rotations and irrational rotations. For instance, there you do know that irrational rotations are dense, and then you would like to understand how is it distributed, and then it comes the Diophantine properties of the irrational rotations that you have. The other groups that you can think of is like SLNZP. It's a compact group. You take SLNZ, for instance, inside SLNZP. It's a dense subgroup, and you want to see how dense it is. How is it distributed? Or you can think about SUN, and then you can cook up a dense subgroup inside that, and you can ask again, how is it distributed? So these are the kind of questions that you want to understand. Okay, but let's see, how do I want to formulate this in mathematical terms? One way to go about it is using random walk. So I start with omega, and then I do random walk with respect to this finite symmetric set, and I ask myself, what is the limiting law? So let's actually, again, recall what is random walk. I know that you know, but okay, I start with this. This is essentially the counting probability measure on the finite set that we have. So it is 1 over the size of omega if G belongs to omega, and otherwise it's 0. So this is the first law. And then I start doing random walk with respect to this. For instance, in the second step, so what's going to be the probability law in the second step? In order to reach to a point, I should start with G1 and then multiply it by G2, both of them inside omega. And then the probability law would be, so we usually denote it by this. So we should write down G as product of two guys, and then multiply the probability of reaching to the first one and the second one. If you haven't seen it, this is called the convolution of this guy by itself. So this is the convolution of this probability law by itself. So in general, you can talk about convolution of this with any other function. So that would give you another function on G, and this is by definition. So, and you can do it not only for this, but for any measure mu. So let's assume that measure has, this measure has finite support, then it's easier. I don't have to write integral. So this would define an operator on different kind of functions on the group G. Okay, and what I'm saying is that the second step, the probability law after the second step random walk, is just a convolution of this probability measure by itself, and then you can repeat this again and again. So the probability law after L step random walk is the L convolution, the L-fold convolution of this guy by itself. Okay, so now, so this means in order to understand the random walk, we need to understand the convolution of this measure by itself. You have to understand how it works. And one way to do it, okay, so and what is the question? What is the hope? The hope is, okay, first of all, I should say that these elements of gamma cannot go outside of its closure. So we are trapped within that closure. And now within that closure, one might hope that it gets equidistributed. So meaning this random walk converges to the Haar measure of the closure. Okay, so this is the kind of question that you would like to understand. So under what conditions? This actually converges to the probability, the probability Haar measure at the closure to the closure of gamma, where this is where. And if you probability Haar measure and gamma bar. So this is essentially, so what is it? It is a probability measure on gamma bar, which is gamma bar invariant. So it means there is no, it's completely flat. So every point looks like the other point. Okay, so we want to say that these random walks do not distinguish, do not discriminate between the points within the closure. So this is one question. The other question is, do we have, if such a thing happens, do we have a control on the error rate? So can we say anything? Can we say anything about the error rate? So now you have to put different norms, but I just write it in a loose term. Okay, so these are the general questions, so general that probably you cannot answer. So now let's make it a bit more specific. Let's see under what condition actually we can understand this. Let's come back to this operator and think about it as an operator on L2 of G. Okay, I start with L2 of G and think about this. So let's say 2 omega from L2G to L2G. G omega F is convolution of this guy and F. So this means that when I want to understand the random walk, I have to understand the L power of this operator. So we need to understand and as all of us know from linear algebra, if you want to understand a matrix raised to power L, then we have a best understanding if this guy is in diagonal form. Okay, so if we can make it diagonal, then we are in good luck. And okay, so what do I know about this operator? Okay, so I assume that omega is actually symmetric. That would imply that this operator is actually self-adjoint. And the other thing is that this is an averaging kind of operator, so its norm cannot be more than 1. And the constant function is actually fixed under this. So let me write down these kind of things that I wrote and that I just said. So T omega is a self-adjoint operator, and okay, so its operator norm is at most 1, and the constant function. Okay, so actually I'm going, as I mentioned, we do not care about the entire G. I care about the gamma bar, because at the end of the day, it's trapped in its closure. And we know that the constant function on gamma bar is actually fixed. The other thing that you should notice is because I'm focusing on gamma bar, the only function that is fixed under this operator is the scalar function. So if something is fixed under this, because the group generated by omega is dense inside gamma bar by definition, so if I know Tf is f, that would imply that f is a scalar. Okay, so multiplicity of the eigenvalue 1 is actually 1, okay, because I'm focusing on the closure of the group. Okay, so now the good point about self-adjoint operators is that we can actually diagonalize. Now that we can diagonalize them, we can think about the L power. And okay, so but now we have to be a bit careful from linear algebra. Here the spectrum is not necessarily discrete, so in principle we might be able to get closer and closer to 1. And in that scenario, we do not get a very good understanding of this guy, because this guy gets closer to 1 as well. But if we do have actually a spectral gap, if there is a gap between 1, then as we raise it to power L, this guy, the other, getting closer and closer to projection to the eigenvalue 1. Okay, and that's exactly the integral of the function with respect to the Haar measure, which means we get to answer both of these questions. So this would converge to the Haar measure, and with exponential rate, which is dictated by the spectral gap. Okay, so let's denote. Let's make this notation definition. So that lambda of omega. So here, this is a convention that I'm choosing because of this convenience. I'm not assuming that the group generated by omega is dense inside G, but this notation means that I just focus on the closure. Okay, so this makes the notation less messy. So this means, by definition, so I will actually define it as the operator norm of T omega restricted to the L2 of gamma bar, but I forget about the constant function, orthogonal to the constant function. Okay, I define this to be this. And as I said, because this is a self-adjoint operator, this is the same as the supremum of absolute value of lambdas, where lambda is in the spectrum of the operator T omega, and lambda is not 1. So okay, one has to, yeah, so a priori minus 1 might be in the spectrum, but yeah. So if minus 1 is there, I'm gonna get 1 for this. Okay, and I say, so this is a notation, and I say that so gamma generated by omega, the action on G. So again, this is the convention for that I choose. The proper way of saying it is that the action on gamma bar, but I rather write it like this. And I say this guy has a spectral gap. has a spectral gap if this is strictly less than 1. Okay. And as I discussed, in this kind of scenario, if this happens, then we are in the best shape in order to, in the understanding of this. Then not only this guy converges to the Haar measure, but in fact it converges with exponential error rate. So, and the exponent is just this. Okay. Okay. Now, nice. We have this definition, but is there any example? Okay, so I will start with more classical kind of examples. I start with a cheating example. So this is the cheating example. Okay, but before I give you a cheating example, let me actually rephrase this property in terms of the so-called almost invariant functions. Okay, so alternative definition. Okay, so let's think about this operator. The operator is essentially averaging operator. We are averaging on the left translates of the function. We are averaging on the left translates of the function. Let me write it down. Notice that t omega of f. So when I applied to a point g, so this is a function, and I want to understand what is the value of this function at g. By definition, it is 1 over the size of omega, sum of f of gamma inverse g, where gamma belongs to omega. So it is essentially the average of the left translates of f applied to g. Okay, so we are looking at the left translates of the function f and then apply it to g. And then when we say that we want to shrink it, so essentially this says that if f is orthogonal to the constant function, we are supposed to shrink this. This means that these guys cannot be close to f. So if all of them are close to f, then the average is going to be close to f. If I'm supposed to shrink it, at least one of them cannot be close to f. Okay, this is called the so-called. So there is no almost invariant functions. So let me write it down. So then, if lambda omega g is strictly less than 1, then for every f inside L2 of gamma bar orthogonal to the constant function, so at least one of the guys inside this omega moves f away from itself. Okay, so now I have to normalize it by the norm of f, or alternatively I can put it on the other side to avoid the 0 case. So at least one of these guys is going to be more than epsilon f, where this epsilon depends on lambda. It doesn't depend on f. That's the important part. Where epsilon depends on. Okay. So again, loosely speaking, this says that L2 gamma bar does not have epsilon invariant, epsilon almost invariant function. Okay. And in fact, the inverse is also correct. Okay, so now the cheating example is groups with property T. So what is that? So this means I'm forgetting about G at the moment. I'm saying if I start with gamma, if gamma has property T, I will tell you what it is, and you will see immediately that it's a cheating way of getting example. Then you would get so then what is it? So what is this? It says not only you look at this L2 of gamma bar naught, you take any unitary representation with no fixed point, then it's not supposed to have epsilon almost invariant function. Okay, so it seems I'm killing this with a much stronger property, and I'm doing it. So it has property T, and it means, i.e., if I take any unitary representation, if H has no fixed point under gamma, so i.e. there exists some epsilon, such that if this guy has no fixed point, then it has no epsilon almost invariant function. Okay, so far I didn't provide any example. So now the question is, do I have any such group? And yes, Kajdan provided lots of them. So if gamma is a lattice in a so-called higher rank simple group, in a higher rank simple B group, then we have this. Again, okay, so if you don't know what that means, so SL and Z you can think of. Then gamma has T. Again, you can think about, okay, for instance, SL and Z. If n is at least 3, this is a lattice inside SL and R. I mean, this is always a lattice inside SL and R, but if n is at least 3, then it is in the higher rank. Or another example that I'd like to mention is, think about the quadratic form in 5 variables. Minus and think about the orthogonal form. I mean, this is the quadratic form, and then think about the linear forms that preserve this quadratic form. And look at the matrices with entries inside Z root 2. Then you can embed it into, and you can ask for the real solutions. And that would be, because it has 2 negatives, I mean 2 positive and 3 negatives, it would be inside this, and the real rank of this is 2. So again, this is another example. Okay, so these are 2 examples of such thing. So in particular, so now in order to get in the setting that we had a compact group, and a dense subgroup inside a compact group. For instance, here you can think about SL and Z sitting inside SL and ZP. Or you can think about SL and Z sitting, in fact, in the product of SL and ZPs. So in particular, we get this result, that the action of SL and Z on the product of SL and ZPs has a spectral gap. But here, okay, so this you can embed it here. This is a compact group, and because this guy has property T, this has a spectral gap. Or you can, okay, so now I have to give you a compact group for this. You can think of, you can embed it via the Galois conjugate and put it plus, plus, plus. So we would embed it inside SO5, and that's a compact group. So that guy, SOQ 0.2 acts on SO5, and this action has a spectral gap. Okay, so these are 2 examples, more classical kind of examples that you have here. Okay, but so this has a spectral gap, and so far I just told you for this. But I mean, as you can see, I'm killing it. I mean, I'm assuming that any unitary representation has this property and so on. I'm not telling you anything about gamma, I mean, anything about G. We started with a compact group G. We wanted to understand the subgroups of G. One example of that phenomena is Selberg's result. So let's go to the n equals to 2 case. But before that, let me actually point out that, for instance, if gamma can be mapped into Z, then you can think about rotations of very small angle. And then this means I'm not moving it much. So Z does not have property T. So anything that maps into Z does not have property T. So free group does not have property T. So SL2Z cannot have property T because it's essentially free group. So you cannot talk about this using Kazhdan's property, but this is due to Selberg. I mean, Selberg's result actually implies this. He didn't directly thought about this, but he dealt with this. So he shows that SL2Z also has the same property if you think about this action. So there is something, I mean, specific about this. The arithmetic behind this helps him to show that this guy has a spectral gap. Okay, so, and in fact, this line of argument, this arithmetic property of the groups had been extended by lots of people had been involved with this kind of question. And now we have a very good understanding of that, the complete understanding. And this is the theorem. I'm mentioning some of the key figures. So in general, this talk, I should apologize to lots of people because I will not be able to cover all the results. There are lots of mathematics behind them. So I will mention just few key players. I mean, I've already mentioned Kazhdan. Okay, maybe I should have mentioned Selberg before this, but okay. Then Berger and Sarnek. And then Clausel and Clausel and Ulmer. So what is the result? They say if G is defined by equations over Q, and let's assume that it's semi-simple, it means that it does not have a normal subgroup that is upper triangularizable with 1 on the entry. Then if I look at the entries of this guy that comes from Z joined with the guys whose denominator is a power of Q0 or multiple of Q0, then this can be embedded into the product of GZPs as long as P doesn't divide Q0, and this action has a spectral gap. Okay, so in the arithmetic setting, now we have the best understanding. Before I go beyond arithmetic, let me mention a few applications. Why should we care about this? I didn't mean to be so dramatic, but yeah, it happened. So, okay, maybe the first one of the first applications would be explicit construction of expanders. So what are expanders? Expanders, so this is an application to combinatorics. So what are expanders? So in communication or so in theoretical computer science, so I cannot do the justice on application of expanders, but you do need sparse graphs, you do need sparse graphs that are highly connected. So, but I have to tell you what it means. Sparse, highly connected graphs. Okay, so one way to think about sparse, so one way to formulate it is saying, I'm going to have a family of k regular graphs where k is fixed. As the size of the graphs gets larger and larger, this is going to be very sparse. So I think about a family of k regular graphs. I mean, in practice, you do not want to restrict yourself to k regular because most of the graphs in applications are not actually regular. But anyway, so I'm in the pure side. So a family of k regular graphs. By fixing k, I'm going to get a sparse graph. Now I have to tell you what this highly connected means. And I'm not going to go through the better way, combinatorial way of thinking about it. I'd rather go through the random walk point of view because it's connected to the way that I started the talk. So, okay, so I'm going to convince you why random walk is important. I try to convince you. So think about this example. So I usually say this in my classes. So let's say I am in a city, and this city has a bridge. And there is, in the news, that there is a drunk guy with a gun. And you try to avoid this guy. So you have the best chances would be that to go to the other side of the bridge. Because, I mean, this guy doesn't understand. So he goes randomly. You do not understand where he is going. So if you are there, you have a better chance. And you are doomed if your city is very connected. Because then, after half an hour, you have no idea where this guy can be. Okay, so he goes randomly anywhere, and any point can be something like any other point. So in this scenario, this is not very well connected. So if I cut this, then I'm cutting the whole thing. But if this is very well connected, you cannot understand, you cannot predict where this guy is going to be. So this is why you can detect highly connectivity using random walk. So essentially, you want to say that in logarithmic steps, you do not have much prediction where this guy is. So the probability law of random walk after logarithmic steps is very close to the stationary measure, but in the k regular case, the stationary measure is equidistribution. Okay. So that means highly connected. And you can see now the connection with random walk in compact group. So for instance, if I start with a mother compact group like where it has lots of finite quotients, so if I get equidistributed here fastly, then in all of these quotients, I'm going to get equidistributed fastly. So this means that I'm going to get lots of Cayley graphs through then, I mean, lots of expanders through the Cayley graphs. And that is Margulis's explicit construction. So Margulis showed that if, so he, in that case, he wanted to give a very concrete example. So he started with a group with property T. Then this would imply that the Cayley graphs are finite quotients of this as n varies among the normal finite index subgroups, form a family of expanders. So another example that I can mention is in, you see, so I picked these examples on purpose. Now you can see from here, I can look at the arbitrary, I can look at the arithmetic quotients. I can look at SLN Z mod out by MZ, and then I'm going to get expanders. And how about this one? Does it have an application? Yes. So this is the so-called Banach-Ruziewicz problem. So Banach observed that, in fact, you can, okay, so probably all of you heard that you can cut the circle and put it in infinitely many pieces and then put it together and get two circles. Okay, so this means that there are finitely additive measures on the circle that are rotation invariant, but they are not Haar measures. So that would imply that in particular. Then he asked, do we have this phenomena for Sn if n is more than 1? So the question is, if nu is a finitely additive measure on Lebesgue sets, yes.
I mean, the bag is what you saw, but it is still unsolved for Borel.
Yeah, but I think he has for Lebesgue. I don't know. Yeah,
It is unsolved.
For Borel it is. Yeah, but I think yes. Okay, but I want to say something that is solved. Yeah. 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 Yes. Okay. So yeah.
Yeah, he probably knows the bag because he was thinking of Banach.
Yeah. I think in the same article, actually, Banach is proved, yeah. So nu is finitely additive measure on Lebesgue sets of Sn. And the assumption is that nu is rotation invariant. Then the question is, does it imply that it is the Lebesgue measure? N should be at least 2. Okay, so it was known. I mean, I'm embarrassed to say that I forgot who proved it. Maybe so that it was known that if you can provide, so you see SON plus 1 acts on this, and it was proved prior to Margulis's observation. Yes, yeah. And so it was proved that if you can create a single operator with a spectral gap inside SON plus 1, then the answer to this question would be yes. Okay, and then Margulis so quickly observed that. And Sullivan, yeah, independently. They proved more. So Margulis also answered this not for a sphere, but for Rn as well, independently. That the answer is yes if n is at least 4. If n is at least 4. And they use this. For instance, you can use this for 5, this kind of example. This guy has a spectral gap.
You said something if SO plus 1.
So if there is, so it was known before this that if you can find, if there is gamma inside SON plus 1 that is dense, and this action has a spectral gap. Then the answer is yes. I don't know how to write his name. So yeah, so it was in 81, and RO is the initials, but and there is an S I think afterward, but yeah. So yeah, so then, but as I said, the importance is that they provide a more general setting, not only for this, for simple groups as well, and not only for sphere, but for Rn as well, and so on. Okay, but this is another kind of applications that the spectral gap can provide you. But let's go back to this result. So it's still here you see that, okay, so even for this group, for this compact group, we are very restrictive on the gamma. It's not like picking some finite set and asking, do we get a spectral gap or not? I need to pick this specific gamma in order to get a spectral gap. Now, here is the so-called super-approximation conjecture. Thank you. Two T's? Thank you. Okay, so now, actually, before I write down the conjecture, let me point out that, I mean, in all of these formulations that I mentioned, I said you have this gamma, and then it acts on some compact group, but then I have to focus on its closure. And I always threw it under the rug, what is the closure? So even in this kind of scenario, so let's say I start with gamma inside this product, what can I say about the closure? Is it going to be an interesting group? How large it is? Under certain algebraic conditions, strong approximation actually tells us that this is going to be an interesting group. This is going to be an open subgroup of this. Okay, so this is a strong approximation. Let me write down. I'm not going to write down the technical conditions because that's not important for us at the moment. A strong approximation. The philosophy is more important. So a strong approximation says under certain algebraic conditions, the closure, so if I start with gamma, a subset of GLN Q, if it's finitely generated, this is essentially inside. The denominator cannot have more than finitely many primes. So I start with a finitely generated subgroup of this. And then I ask, what is the closure of this inside product of GL and ZPs, if P doesn't divide Q naught. And under certain algebraic conditions, it says that this closure can be described through the Zariski closure of gamma. So if you look at all the equations, polynomial equations that gamma satisfies, clearly this cannot be outside of that. Now, inside that, it's very large. So it's a finite index subgroup of that. Okay, this is, so then this is an open subgroup of product of G, you see this bold guy, P, where this is the Zariski closure of gamma in GLN. Okay, this is just a fancy way of saying that I look at it over Q. Okay, so now you see the closure is dictated by the Zariski topology. Now the question is, is this analytic property of the random walk, is this guy is also dictated by the Zariski closure? And this is the content of super-approximation conjecture. And now you see the name. Okay, so what does it say? It says, again, you start with a finite symmetric subset of GL and Q. And because it's finite, it's essentially inside this. And then you look at the group generated by this. You look at the action of this on the product of GL and ZPs. Now you ask yourself, what is the necessary and sufficient condition for this to have a spectral gap? And the answer should be that this has a spectral gap if and only if the connected component of the Zariski closure is perfect, which means it's the same as its commutator. Okay, so this is the conjecture. In this form, it is due to myself and Varya. There is another stronger form due to Alex Lobotsky, but I don't dare to go there. So Alex goes to finitely generated rings, but I stay here. Okay. Now, what do we know? Okay, so I will not, again, I apologize, I will not mention all the results related to this. In the past decade, we had lots of activities on this, especially in the remaining 10 minutes. I cannot do that. But I do have, I have to start with Burg and Gambert's work on SL2FP. That's the seminal work on this. So the whole thing started with the work of Burgan and Gambert. Say it again?
It actually goes to the quarter after.
So it's, I have, no, yeah, okay. So then what should I do?
Why don't you state that? Yeah, state this and then
Okay.
continue the other.
Okay, I can do that. So Burg and Gambert's work is, it says that if gamma, okay, so they proved stronger than this. In fact, their method is much more important than just the result, but the result is extremely important as well. So if you start with a finitely generated subgroup of SL2Q, so again, it's inside SL2 C1 over Q naught, then they say that if I look at the soup, so they get spectral gap, uniform spectral gap on the finite quotients of omega and SL2FPs. So these would induce random walks on the finite quotients of SL2FPs. So then they say, so this is less than 1 as soon as the Zariski closure is the entire SL2. There is no restriction. What was the question?
Is there a restriction on n here?
No, no. Yeah, so this is general. Yeah, so this they prove this. You should, okay, so this is, okay, you should see that this is, okay, this seems much restrictive, and it is much more restrictive. So this is, if you know this, if you know that this random walk on this mother group has a spectral gap, then that gap descends to all the quotients of this guy. So in particular, you get mod arbitrary the same gap. But here we are saying that if you just look at it mod primes, you get uniform gap. Okay, but as I said, the technique is much more important. My aim was to mention more results in this lecture, and then tell you about how they go about the proof in the next lecture. But probably I will not be able to tell you. Okay, I have to decide which one to say next.